Picture this. Your child sits down with a handful of wooden tiles, arranges them in a careful sequence, presses a button, and watches a little robot navigate across the floor exactly as they planned. No screen, no app, no Wi-Fi required. They just programmed their first algorithm using nothing but their hands and their brain. I'm Dr. Priya Mehta, and today we're talking about screen-free coding kits that teach real programming logic without adding a single minute to your family's daily screen time.
You're listening to the STEM Lab podcast. Quick note before we jump in, everything you hear in this episode, all the research, the recommendations, the advice, that's been written and verified by real people, real experts in STEM education. The voice you're hearing right now, though, that's AI generated. We're using this approach so we can bring you more content more consistently while keeping the quality high. Just wanted you to know how this works. Now, if you've been listening for a while, genuinely, thank you. I know there are a million podcasts out there, and I appreciate you choosing this one. And if you're brand new here, welcome. I think you're going to find this useful. We release new episodes every Monday, Wednesday, and Friday, covering toys, kits, strategies, all kinds of STEM learning tools for families. Let's get into today's episode. You want your child to learn programming logic without tacking on another hour of screen time to their day. I completely understand that tension, wanting to build their computational thinking while protecting their developing eyes and attention spans. The best screen-free coding kits for kids offer a guilt-free alternative, tangible, hands-on tools that teach sequencing, loops, conditionals, and debugging through physical manipulation rather than pixels. So what exactly are screen-free coding kits? They're physical learning systems that teach programming concepts like sequencing, pattern recognition, logic structures, debugging, and algorithm design, all without requiring computers, tablets, or smartphones. These kits use tactile components, wooden blocks, directional tiles, puzzle pieces, cardboard programming cards, fabric mats, or small robots with mechanical buttons to represent coding instructions. The Cubetto playset pioneered this approach with its wooden robot and block-based programming board, demonstrating that children as young as 3 can grasp fundamental coding logic through touch and spatial reasoning. Unlike traditional coding toys that require screen interfaces, these kits operate through direct physical cause and effect. Your child places a sequence of command tiles, presses a button, and watches their creation execute in the real world. What makes these tools genuinely educational rather than simply screen-free alternatives is their alignment with computational thinking frameworks. They're not just avoiding screens, they're deliberately building the cognitive scaffolding children need before they ever touch text-based code. The American Academy of Pediatrics has documented serious concerns about excessive screen time in early childhood, making these physical coding tools particularly valuable for families managing tech exposure while maintaining STEM skill development. The best screen-free coding kits for kids create what developmental psychologists call low-floor, high-ceiling learning environments. Easy enough for beginners to start immediately, complex enough to challenge growing minds across multiple developmental stages. Now, let's talk about how these kits actually work. They translate abstract programming concepts into physical actions your child can see, touch, and manipulate. The mechanism varies by design, but all screen-free coding systems share 3 core components: command representation, sequence building, and execution feedback. First up is command representation through physical objects. Each kit uses tangible objects to represent programming instructions. The Code and Go robot mouse activity set employs directional arrow cards, forward, backward, left turn, right turn, that children arrange in sequence. Robot Turtles uses card-based commands, where each card type represents a different movement or action. More advanced kits, like wooden coding blocks, use color coding, symbols, or shape variations to differentiate between movement commands, loops, and conditional logic. Your child learns to read these physical tokens the same way they'll later read if, while, or for statements in Python. The cognitive load is significantly lower because they can hold the instruction in their hand, examine it, and physically move it around while planning their algorithm. After selecting individual commands, children arrange them in specific orders to create algorithms. This physical sequencing is where the real learning happens. Your child experiments with different arrangements, discovers that order matters, a foundational programming principle, and develops debugging skills when their sequence doesn't produce the expected result. Many kits include loop representation, tiles or cards that indicate repeat this section 3 times, teaching iteration without abstract notation. The tactile nature means your 6-year-old physically groups the commands they want to repeat, creating a concrete mental model of how loops contain other instructions. Function creation appears in advanced screen-free kits through color-coded sections or dedicated subroutine cards. Your child builds a small sequence, labels it as a reusable function, and then calls that function within larger programs, exactly mirroring how procedural programming works in industry-standard languages. The magic moment arrives when your child executes their physical program. In board game formats, they manually move a game piece according to their coded sequence. In robotic kits, they press a go button and watch a small robot follow their instructions. The immediate visual feedback, success or collision with an obstacle, creates natural debugging opportunities. This execution phase develops what computer scientists call tracing skills, the ability to mentally simulate what code will do before running it. Your child learns to visually trace their command sequence, predict the outcome, and identify errors in their logic. These are precisely the skills professional developers use when debugging complex code, but your child builds them through play rather than frustration at a screen. When programs fail, and they will often, the physical nature makes errors visible and comprehensible. Your child can see exactly which command in the sequence caused the robot to turn the wrong direction. They develop resilience and systematic problem solving without the cognitive overload of syntax errors, missing semicolons, or cryptic compiler messages. The developmental benefits extend far beyond simply reducing screen exposure, though that alone offers significant advantages for attention span, sleep quality, and eye health in children under 8. Concrete operational thinking develops most effectively through physical manipulation. Between ages 4 and 11, most children function in what developmental psychologist Jean Piaget identified as the concrete operational stage. They understand concepts best when they can physically interact with them. Abstract symbols on screens require cognitive translation that physical objects bypass entirely. When your 7-year-old moves a forward 3 spaces tile, they're building neural pathways that connect the abstract concept, instruction, with concrete reality, movement, through their own hands. Screen-free coding also addresses the executive function challenge inherent in traditional programming. Learning to code on a computer requires simultaneously managing syntax rules, abstract logic, spatial visualization, and tool interfaces. That's overwhelming cognitive load for developing brains. Screen-free kits isolate the logic component. Your child focuses purely on algorithmic thinking without battling keyboard skills, mouse precision, or software navigation. I've watched this transformation in my own home. My 6-year-old daughter struggled with early Scratch projects because she couldn't yet manage the block dragging interface precisely enough to express her ideas. Switching to wooden coding tiles removed that friction entirely. She could finally focus on the logic she wanted to create rather than fighting the input mechanism. These kits also create natural collaboration opportunities that screen-based coding often inhibits. Multiple children can gather around a physical coding board, discuss strategy, point at specific commands, and jointly debug a sequence. The social learning that emerges, negotiation, explaining reasoning, collaborative problem solving, builds communication skills that professional programmers desperately need in team environments. Perhaps most importantly, screen-free coding prepares children for the transition to text-based programming languages without the jarring leap that causes many young learners to abandon coding entirely. They arrive at Scratch or Python already understanding sequencing, loops, conditionals, and debugging. They're simply learning new notation for familiar concepts. Let's look at the different types and variations of screen-free coding kits. The screen-free coding landscape has diversified significantly as manufacturers recognize the demand for unplugged STEM learning. Understanding these categories helps you match tools to your child's developmental stage and learning style. Board game formats like Robot Turtles and Codemaster transform programming into competitive or puzzle-solving play. These require no batteries, no setup beyond unpacking components, and scale difficulty across hundreds of challenges. They're ideal for families seeking truly zero-tech options and work beautifully for children ages 4 through 10. The limitation? They don't provide the immediate robot execution feedback that makes errors instantly visible, requiring instead parent facilitation or self-checking. Programmable robot systems offer the middle ground, combining physical programming with robotic execution. Kits like Code and Go Robot Mouse or Cubetto use battery-powered robots that execute physically programmed command sequences. These provide the critical feedback loop. Your child watches their code run in real space while maintaining the tactile programming interface. Power requirements are minimal, usually 3 to 4 AAA batteries, and they're durable enough for years of repeated use. These excel for ages 5 through 9 and prepare children particularly well for transitioning to Arduino robotics platforms. Wooden block and tile systems are the premium options, using laser-cut wood or high-quality plastic tiles that represent commands through symbols, colors, or shapes. These focus heavily on the cognitive sequencing aspect, without robotic components, making them the most portable and durable option. They're also infinitely expandable. Your child can combine multiple sets or create their own additional command tiles. The trade-off is they require more imagination and parent facilitation to execute programs, though this guided interaction offers developmental benefits for younger children, ages 3 to 6. Fabric mat and card-based hybrid systems combine floor mats printed with grids, mazes, or challenges with programming cards or tiles. Your child arranges cards to code a path, then physically walks it themselves, or directs a toy or robot along the route. This full-body engagement adds kinesthetic learning to the cognitive work, particularly valuable for children who learn best through movement. The fabric components are machine washable and remarkably durable, though they require dedicated floor space during use. Let me address some common questions parents have about these kits. What age should my child start with screen-free coding kits? Children can begin screen-free coding as early as age 3 with simple directional sequencing kits that use 4 basic commands: forward, backward, turn left, turn right. At this stage, they're building pre-coding skills like following multi-step instructions and understanding cause and effect rather than formal programming concepts. Most children develop the pattern recognition and abstract thinking needed for loops and conditional logic between ages 5 and 7, making that the optimal window for introducing more complex screen-free programming concepts that directly prepare them for eventual text-based coding. Will screen-free coding actually prepare my child for real programming? Screen-free coding builds the exact cognitive foundations that professional programmers use daily: algorithmic thinking, debugging methodology, pattern recognition, and the ability to break complex problems into sequential steps. What it doesn't teach is syntax, the specific notation of Python, Java, or JavaScript. Think of screen-free coding as developing fluency in the grammar and structure of a language before learning to spell words on paper. When your child eventually transitions to Scratch or Python programming, they'll already understand what loops do, why order matters, and how to systematically debug errors. They'll just be learning new symbols for familiar concepts, which is significantly easier than learning both simultaneously. How long do screen-free coding kits remain useful before my child outgrows them? Well-designed screen-free kits typically provide 18 to 36 months of progressive learning before children need to transition to screen-based environments. The longevity depends on three factors: the kit's complexity ceiling, your child's pace of development, and whether the system supports expandability through add-on modules or custom challenge creation. Budget kits with limited command sets often max out after 6 to 8 months, while premium systems offering functions, nested loops, and conditional logic can engage children from age 5 through early middle school, especially when combined with advanced unplugged coding games that build on the same physical programming principles. Do screen-free coding kits require subscriptions or ongoing purchases of consumables? The vast majority of screen-free coding kits function as one-time purchases with no recurring costs. They use durable, reusable physical components, wooden blocks, plastic tiles, fabric mats that last through multiple children with normal wear. The exceptions are rare subscription boxes that deliver monthly screen-free coding challenges, though these are distinctly different investment models than purchasing complete kits. Battery-powered robotic components require occasional AAA or rechargeable battery replacements, budget around $10 to $15 annually for heavy use, but the programming interfaces themselves never require consumables. This makes them significantly more economical than app-based coding platforms with annual subscription fees. Can my child use screen-free coding kits independently, or do they need constant parent supervision? Independence levels vary significantly by age, kit complexity, and your child's prior experience with structured challenges. Children ages 3 to 5 typically need parent facilitation to explain challenge goals, help interpret symbols, and celebrate successes. Budget 20 to 30 minutes of engaged co-play. By ages 6 to 8, most children can work independently for 15 to 40-minute sessions with board game formats or familiar robot kits, checking in with you only when stuck or ready to demonstrate their solution. The physical nature of these kits naturally encourages independence compared to screen-based coding because there's no software navigation to master. Your child can see all available options simultaneously and physically manipulate them without accidentally clicking into confusing menus or deleting their work. Now let's talk about building a progressive learning path with screen-free coding. The true power of screen-free coding emerges when you view these kits not as isolated activities, but as interconnected steps in a sequential skill-building pathway. This progression mirrors how professional computer science education scaffolds complexity, but adapted for developmental readiness in childhood. At the foundation stage, ages 3 to 5, you're not actually teaching coding, you're building the prerequisite cognitive skills. Your preschooler needs to develop sequential thinking, understanding that order matters, spatial reasoning, visualizing movement through space, and basic pattern recognition. Simple kits with 4 directional commands and clear cause and effect relationships work beautifully here. Look for kits that limit command vocabulary to 4 to 8 options maximum. More choices overwhelm developing executive function capabilities. Your goal isn't complex programs, it's building the muscle memory of thinking through steps before acting, a habit that serves all future programming work. During the sequencing mastery stage, ages 5 to 7, children are ready to create longer command sequences, 10 to 15 steps, and encounter their first major programming concepts, loops and debugging. They should spend substantial time with challenge-based kits that offer 40 to 60 progressive problems, each slightly more complex than the last. This is where screen-free coding demonstrates clear advantages over screen-based alternatives. Your 7-year-old can physically rearrange command tiles, testing different sequences without losing their previous attempt or struggling with digital interfaces. They develop genuine debugging skills, the systematic approach to finding and fixing errors, rather than random trial-and-error clicking. Watch for the milestone where your child begins to trace their code mentally before executing it. That's the sign they're internalizing the logic rather than just playing with physical objects. It usually emerges after 15 to 25 hours of accumulated practice time. The logic structures stage, ages 7 to 9, is when advanced screen-free kits introduce conditional logic, if-then statements, and nested loops, loops within loops. These concepts represent the genuine complexity threshold, the point where your child's programs begin to resemble actual code structure rather than simple movement sequences. Kits at this level often incorporate multiple solution paths for the same challenge, encouraging optimization thinking. Can you solve this puzzle with fewer commands? Can you use a loop instead of repeating the same sequence? This optimization mindset directly prepares children for the algorithmic efficiency thinking that distinguishes strong programmers. This stage typically lasts 12 to 18 months before most children outgrow the complexity ceiling of physical coding systems. You'll notice increasing frustration when they conceive of programs more complex than their screen-free kit can express. That's your signal to begin the transition to Scratch or block-based screen programming. The bridge to screen-based programming, ages 8 to 11, shouldn't be an abrupt abandonment of screen-free tools. Create a bridge period where your child uses both physical coding kits and beginner screen-based platforms simultaneously. They can prototype algorithms with familiar physical tiles, then translate those solutions into Scratch blocks or simple Python commands. This parallel practice reinforces that the underlying logic remains constant, only the notation changes. It's the computational thinking equivalent of learning to write words you already speak fluently. The cognitive load stays manageable because you're isolating the new skill, syntax and digital interfaces, from the already mastered skill, algorithmic logic. Children who follow this progressive path typically demonstrate stronger debugging skills, better planning before coding, and more resilience when facing complex programming challenges compared to peers who began directly with screen-based coding. They've built the mental models first, then layered notation on top, the natural sequence that works with childhood cognitive development rather than against it. Moving on to technical considerations, when evaluating these tools for your home STEM lab, practical specifications matter as much as educational design. Let's examine the infrastructure requirements and durability standards that determine whether a kit will thrive or frustrate in actual family use. For power and connectivity requirements, board game formats need zero power, fully functional out of the box with no batteries, charging, or electrical infrastructure. This makes them ideal for travel, outdoor use, or situations where you want truly unplugged learning without setup friction. Robot-based kits typically require 3 to 4 AAA batteries for the robotic component, with battery life ranging from 8 to 15 hours of active use depending on motor efficiency and weight of the robot. Premium models use rechargeable lithium batteries, eliminating ongoing consumable costs but requiring access to wall outlets for charging, typically 2 to 4 hour charge cycles. The defining characteristic of screen-free coding is the complete absence of Wi-Fi, Bluetooth, app requirements, or cloud dependencies. These kits function in airplane mode forever. There's no software to update, no accounts to create, no internet outage that prevents learning, and no data privacy concerns to navigate. This represents both a practical advantage, true portability, and an educational one, no digital distractions bleeding into focus time. Regarding space and storage footprint, most screen-free coding kits fit within a 12 by 18 inch by 4 inch footprint when stored, making them compatible with standard shelf space or under-bed storage. Active use space varies dramatically. Board games need a 2 by 3 foot table surface minimum. Floor mat systems require 4 by 6 feet of clear floor space for comfortable movement. Robot kits with large challenge mats need 3 by 4 feet of dedicated surface, preferably with consistent lighting since shadows can interfere with simple optical sensors in budget robots. For expandability and progression, the most cost-effective screen-free coding kits support modular expansion through add-on challenge packs, additional command tiles, or compatible accessories. Before purchasing, verify whether additional complexity levels are available as separate purchases, if third-party challenge cards or DIY extensions exist in the community, and whether the manufacturer offers curriculum guides that extend learning beyond the included challenge book. Some premium systems use standardized tile sizes that allow you to create custom commands with blank tiles and permanent markers, essentially creating infinite expandability. This DIY extension capability dramatically extends useful lifespan, particularly for families with multiple children at different skill levels, who can each create challenges for siblings. Screen-free coding kits undergo tremendous physical manipulation. Tiles get dropped, sorted, stacked, and occasionally chewed by curious younger siblings. Durability directly impacts total cost of ownership. Red flags include thin cardboard components that warp after 3 to 6 months, small plastic tiles prone to cracking, common in budget kits under $30, printed symbols that fade or peel, particularly problematic with foam materials, and mechanical buttons that lose tactile feedback after 200 to 300 presses. Durability markers to look for are laser-cut hardwood components 5 millimeters or thicker, injection-molded plastic tiles with UV-stable printing, reinforced cardboard with laminated surfaces, stainless steel or brass hardware in mechanical robots, and standardized AAA battery compartments rather than proprietary rechargeable batteries that become unavailable after manufacturer discontinuation. For safety and age-appropriate design, choking hazards appear in kits designed for ages 5 and up that include small command tiles under 1.5 inches in diameter. If you have children under 3 in your household, this matters for storage and supervision planning. Battery compartment access represents the other common safety consideration. Look for screw-secured battery doors rather than simple friction-fit compartments that curious 4-year-olds can pop open. No screen-free coding kit involves sharp edges, heat generation, or chemical hazards. They represent some of the safest STEM learning tools available, requiring minimal supervision from a safety perspective once age-appropriate kits are selected. Screen-free coding doesn't exist in isolation. It connects to multiple other STEM skill domains, creating natural bridges that reinforce learning across your child's entire technical education journey. For robotics pathway integration, children who master screen-free robot programming kits between ages 5 and 8 arrive at Arduino robotics platforms, ages 9 to 14, with enormous advantages. They already understand how commands translate to physical robot movement, the relationship between sensors, input, and motors, output, debugging methodology when robots don't behave as expected, and the concept of uploading a program to hardware that then executes independently. The leap from physical coding tiles to Arduino IDE's text-based programming feels manageable because the underlying robot behavior logic remains familiar. They're learning C++ syntax, not learning what for loops fundamentally accomplish. That cognitive foundation was already built during screen-free coding stages. For families planning a long-term robotics learning path, screen-free coding between ages 5 and 8, followed by block-based robot programming from ages 8 to 10, followed by Arduino projects ages 10 to 14, creates a remarkably smooth progression with minimal frustration points. The algorithmic thinking skills developed through screen-free coding transferred directly to mathematical problem-solving, scientific experimental design, and even writing organization. When your child learns to break a coding challenge into sequential steps, they're practicing the same cognitive skill needed to solve multi-step math problems or outline a persuasive essay. I've observed this transfer consistently. Children with 40-plus hours of screen-free coding experience demonstrate stronger planning behavior before attempting homework problems in any subject. They pause, consider sequence, identify what information they need, and approach systematically rather than impulsively. That executive function strengthening represents one of the most valuable outcomes of early coding education, regardless of whether your child eventually pursues computer science professionally. While screen-free coding kits themselves aren't industry tools, the programming paradigms they teach absolutely are. Professional developers use sequential execution, commands run in order, learned via basic screen-free sequencing. They use iteration, or loops, repeating commands multiple times, learned via physical loop tiles. Conditional logic, if-then decision structures, learned via advanced screen-free kits with branching. Functions or subroutines, reusable code blocks, learned via color-coded command grouping, and debugging methodology, systematic error identification and correction, learned via physical program tracing. Your 8-year-old who can skillfully debug a 20-command physical program has already internalized the core methodology that professional developers use with 200-line Python scripts. They've just internalized it through play rather than frustration at syntax errors. When they eventually transition to teaching AI and machine learning concepts in late middle school or high school, the algorithmic thinking foundation from screen-free coding years earlier makes those advanced concepts significantly more accessible. Computer science education researchers consistently find that the strongest predictor of success in advanced programming isn't early exposure to code syntax, it's early development of computational thinking, precisely what screen-free coding builds. Even well-designed screen-free coding kits encounter friction points in real family use. Here's what I've observed across hundreds of families, along with practical solutions that maintain learning momentum. One common challenge is frustration during the initial learning curve. Your 6-year-old confidently attempts the first few challenges, succeeds easily, then hits a complexity wall around challenge 8 to 12 where solutions aren't immediately obvious. Frustration emerges quickly, sometimes with the dramatic announcement that coding is too hard or this is stupid. What's actually happening is they've exhausted their pattern recognition shortcuts and encountered genuine problem-solving requirements. This is the learning zone, but it's uncomfortable. The solution is to step back to challenges 2 to 3 levels below the frustration point and introduce scaffolding questions instead of solutions. What does the robot need to do first? If you could only use 3 commands, which 3 would you pick? Let's trace this sequence together with our finger. Does it go where you intended? You're building debugging methodology, not solving the puzzle for them. Sessions should end with success, even if that success comes from an easier challenge than where they started. Confidence matters more than speed through curriculum. Another challenge involves sibling skill level gaps. You have a 4-year-old and an 8-year-old who both want to participate, but they're working at dramatically different coding complexity levels. Purchasing separate kits for each child doubles costs. Forcing them to work together creates frustration as the older child solves everything while the younger watches. The solution is to assign complementary roles rather than identical tasks. The younger child becomes the robot who executes commands the older child programs. The older child programs solutions. The younger child identifies bugs by tracing the program before execution. This collaborative structure honors their different skill levels while building communication abilities in both children. For families committed to shared learning, choose kits explicitly designed with multi-level challenges. Many include junior and advanced versions of the same basic puzzle. Declining engagement after initial novelty is another common issue. Week 1 brings enthusiastic daily play. Week 3 brings occasional engagement. Week 6 finds the kit abandoned in the closet, barely touched. This pattern frustrates parents who invested in quality educational tools. What's actually happening is that screen-free coding, like any skill practice, requires contextual variation to maintain engagement. The same challenge format becomes repetitive even when individual puzzles vary. The solution is to rotate between 3 different contexts. First, structured challenge completion from the kit curriculum. Second, open-ended creation, where your child invents their own maze and solution. And third, competitive or collaborative play with siblings or parents, where you race to solve puzzles or work together on complex challenges. This variation maintains novelty while continuing skill development. Schedule coding time rather than leaving it entirely self-directed. Most children need structure to maintain practice consistency, just like music lessons or sports. Finally, unclear progression to the next learning stage can be a problem. Your 9-year-old has thoroughly mastered their screen-free coding kit, working confidently through the most advanced challenges, but when you introduce Scratch or basic Python, they struggle and disengage. The cognitive gap between physical coding and text notation feels larger than expected. The solution is to use deliberate bridging activities rather than abrupt transitions. Spend 2 to 3 weeks where your child creates a program with physical tiles, then recreates the exact same logic in Scratch blocks or simple Python commands. The familiarity of the program logic they just built makes the new notation feel less foreign. Explicitly point out the connections. See how this loop tile is the same as this Scratch repeat block? They both do exactly the same thing, just different pictures. The best screen-free coding kits for kids don't just keep your child away from screens, they build genuine programming logic through the most developmentally appropriate method available: physical manipulation of concrete objects. Your preschooler arranging directional tiles is practicing the same sequential thinking that professional software engineers use when architecting complex systems. The notation differs, the cognitive work remains identical. You're not choosing between screen-free coding and real programming. You're choosing whether to build strong foundations first or rush towards syntax before conceptual understanding solidifies. Every hour your child spends physically tracing command sequences, identifying logic errors in tangible programs, and celebrating when their robot finally navigates the maze correctly is an hour of brain development that makes future programming dramatically easier. Start where your child is developmentally, not where marketing materials suggest. Choose kits that challenge without overwhelming, that offer clear progression paths, and that you can expand as skills grow. Watch for the signs of readiness, when your child begins mentally tracing programs before executing them, when they debug systematically rather than randomly changing commands, when they start creating their own challenges. Those milestones signal deep learning happening beneath the surface of play.
Your child's relationship with technology will span decades. Beginning with wooden tiles and fabric mats instead of glowing screens isn't a limitation, it's a thoughtful choice to protect their development while building skills that transfer across their entire technical future.
That wraps up this episode of the STEM Lab podcast. Thanks for listening all the way through. We'll be back with a new episode on Monday, Wednesday, and Friday. If you found this one valuable, I'd be really grateful if you'd leave us a 5-star rating and write a quick review. It sounds small, but it genuinely makes a difference. It's how other parents and educators find the show when they're searching for this kind of help. And if you haven't already, go ahead and subscribe or follow so you get notified the second a new episode drops. Talk soon.